All right, we are recording. So tonight is actually a pretty short lesson, especially since I cut off the end of it. The end, so the last couple of slides are going to look a little bit different with the the last couple of slides are going to look a little bit different than what you printed off. So you should be able to still go back to previous slides and put notes on those because that's the slide I replaced them with is kind of a repeat of one earlier. You'll see. But I changed things up a little bit because I'm teaching you calculator functions instead of having you do some things by hand because the calculator is your friend. As much as it is tough to learn, once you get to know it, the calculator is your friend. So today, pretty short. I would be really surprised if I was talking past 6:15. So we're going to distinguish between discrete and continuous random variables. It's very similar to the definitions we've already looked at. We're going to look at discrete probability distributions. So we've done some things with continuous. We've done a little bit of this, so this shouldn't be super crazily different. We were doing categorical data with probability distributions, so this isn't much different. We are going to graph discrete probability distributions so you can kind of see what that looks like. Then we're going to look at the mean and the standard deviation of discrete random variables and learn a new term for mean because, we got to call it something different every once in a while. So maybe it's a nickname. It is actually kind of a nickname. And that's what we're doing today. So we only have 19 slides. And normally on a normal night, I'll have 35, 40, 45 slides. So 19 slides are going to go by pretty quickly. So let's get going. All right. So a random variable is it's just a an outcome to a probability experiment. And generally it's numerical. So it could be discrete. It's not usually, we don't usually call a continuous one a random variable, but it's just a variable. We just call it a random variable. And it's something that can be determined by chance. So it could be the number rolled on a dice. It could be how many free throws you made. It could be how many movies you rented this week. It could be how many loads of laundry you did. And then we could like randomly choose from those. So discrete has a finite or countable number of values. We've already talked about that. But specifically, we're looking at random variables here. So it's outcomes of an experiment. Same thing, continuous, outcomes of an experiment. How long did it take you to get to work today? How long does it take you to get to work tomorrow? So if you took all of those every day and I put them all, maybe I would probably use ranges of values and put them in a table and create a probability distribution out of those. It's just one thing that I randomly chose off the top of my head. So continuous has an infinite, can take on infinite number of values, anything in between the 2 points. Generally, if I graphed it, I don't have to lift my pencil. If I graph a discrete, I have to lift my pencil because it's only countable numbers. All right. So taking a look between discrete and continuous, we've done this before. This isn't brand new. So number of light bulbs that burned out in a room of 10 light bulbs, that would be discrete because I can't burn out a half of a light bulb. Number of leaves randomly on a selected oak tree. Once again, this is discrete because even though it's a big number, you can count them. Length of time between calls to 911, this would be continuous. Usually anything that's measured like that is continuous. All right. So a probability distribution, we've already kind of talked about this a little bit. So probability distribution, actually, I already defined it once. So it's the possible values of the random variable and the probability of it happening. So once again, probabilities are always going to be between 0 and 1, and it could be 0 or could be 1. They're always going to be between 0 and 1, and they're going to add up to 1. If I add all of the probabilities in my probability distribution up, it will add up to 1. So it's exactly the same thing that it was before, just this time we're using numerical things. So here's the first one. So the table on the right shows the probability distribution for a random variable X. X is the number of movies streamed on Netflix each month. So this would be like one household, how many movies they streamed on Netflix each month. And so if I add all these values together, they should add up to 1. Uh-oh, just dropped my Apple Pencil. And I'm going to test that real quick. Okay, maybe 0.06 plus 0.58, 0.22 plus 0.1 plus 0.03 plus 0.01. Yep, adds up to exactly 1. So that's good. And these are, so there were 6% of the households watched no movies last month or watched no movies. They probably watched sitcoms or just any kind of binge-worthy shows. It looks like most people watched one. That's 58% watched one. And so this would be my probability distribution. And remember that anything that shows up less than 5% of the time, any occurrence that's less than 5% would be considered unusual. So these two right here would be considered unusual because they occur less than 5% of the time. I know you had a question about this on the hand-in homework that was due today. I think it's due today. All right. We just talked about this. Once again, the rules for discrete probability distribution, all the probabilities will add up to 1, and all of them will be between 0 and 1, and they include 0 and 1. Look at that, I'm already through 8. Okay, probability histogram. So this is exactly the same thing as, whoa, sorry, exactly the same thing as a relative frequency histogram. Exactly the same thing. We just changed the words. It is exactly the same thing. You calculate the probability the same way you calculate relative frequency, and that will go on your vertical axis, and then your outcomes are on your horizontal axis. I have kind of a shortcut histogram in the examples, but it's still the same thing. So here's a normal one. This is the number of movies streamed. So take a look here. I have, instead of relative frequency, it says probability. It's the same thing. Probability and relative frequency have the same meaning. So, and I just created a lovely little histogram here. Any questions so far? It's not like super new information. All right. So here I have basketball player shot a whole bunch of free throws. And the random variable X here. And notice that this, well, it's supposed to be an uppercase X. This is supposed to be an uppercase X. I don't know why it's not in there, but not that you can really tell the difference between an uppercase and a lowercase anyway. Nobody would ever mark you down for using a lowercase instead of an uppercase. It would never happen. Anyway, so our X represents the number of shots made out of each. So each time that they went up to try to shoot 3 free throws, this is how many they made. So this must be a pretty decent basketball player because 51% of the time that person made all 3 of them. So that's pretty good. It's a pretty good basketball player. I would fall in this area probably 80% of the time. I don't have any athletic ability. It's real bad. All right, so this is our probability distribution here. So we're going to graph it. I'm going to show you the shortcut histogram. So I wouldn't use this for like an assignment where you're supposed to show one, but if you were just trying to do a rough sketch of a histogram, this is just kind of a rough sketch of your graph. So it's not an official histogram, but it is a rough sketch that still shows the data. So this is one way to show that. All right, now we're going to do math. This is where the math comes in. And yes, I'm going to teach you some fancy calculator, not even super fancy, but very useful. So the mean. So the mean of the probability distribution right here, this is even though that says DVDs, I don't know why it jumps from Netflix to DVDs when it is the exact same data. The way that we calculate the mean of a discrete random variable is you take the um, the outcome of your data, so the outcome, so my outcome is 0, and you multiply it by the probability of that happening. And you do that with each one. You take the data value, multiply it by the probability, and then add them all together. Yes, you technically don't need to show this one or do this one, but I always do just because it's like it's a good habit to be in to do all of them. So I have 0 times the 6%, 1 times the 58%, and I have each of the outcomes multiplied by their probability, and then you add them all together. So if I shot, let's say many, so let's say that I shot this person, actually, well, this is videos, so Netflix. So if I took a sample of more and more and more houses, like hundreds and hundreds and hundreds and hundreds of houses, as my sample gets bigger and bigger and bigger, the average number of Netflix movies that they watched or DVDs, the average number of movies they watched will approach 1.49. So this is the law of large numbers. If I took many samples, many random samples, and over time, the average number of movies that they rented will approach the $1.49 or 1.49. So that's the average it will approach with many samples. I'm going to show you a graph of that. I'm going to show you to it right there. So here it is right here. So notice in the beginning, these are the samples that I've chosen. And as it goes, I just keep taking the average of it. I did 100 trials of this. As the number of trials increases, my average is going to approach that expected value. That's what this is called. And this right here, this is also called an expected value. Because I would expect, if I did many trials, I would expect the average to approach that. So it's called an expected value. I think I have a definition from it later on, but this is just in my brain where it fits. Okay, so this right here is your interpretation. This is, if I were you, I would underline this. Okay, right there. Because I believe, I'm not sure if it's on the test or if it's on one of the quizzes. I'm not sure where it's found, but there is going to be a question that asks you to interpret the mean of a discrete random variable. And what I would love for you to say is to say something as if we did many trials, it would approach that value. I can't remember if it's the test or a quiz, but I know that there is a question about this. All right, questions so far? See, I get enthusiastic about math, and then my watch tells me, good job on moving, because I'm moving my arms. See, it's just exercise. Teaching math can be exercise. Okay, moving on. I already did that. All right, this is what I just said. Because the mean of the random variable represents what we expect to happen, it is called the expected value. This is the expected value. We would expect our average to approach that. It's actually a very calculus-y thing. It's if you understand limits at all, that's what we would expect. The limit as x approaches, or number of trials approaches infinity, we would expect it to approach that value. Sorry about that. I will back off the calculus. I love calculus. It's fun. All right. Questions? Good. All right. So here's an example. I believe your next hand-in homework has a question very similar to this. So the next hand-in homework that you have will have a question really similar to this. So a term life insurance policy pays a beneficiary a certain sum of money upon the death of the policyholder. These policies have premiums that are paid annually. Suppose a life insurance company sells $250,000 one-year term life insurance policies to a 49-year-old female for $530. According to the National Vital Statistics, the probability the female survives the year is this right here. We're going to compute the expected value. Did I have multiple? No. Okay. So the probability she survives, if she survives, sorry, if she survives, then the insurance company gets $350. There's a 0.99791 probability of that happening. If she dies, why did I write 350 when it's 530?
Oh, I was really confused. Thank you.
You know, it was the same numbers. Oh, see, I just did it again. My gosh, I can't write it. Okay, there you go. 530. Okay. I think that in your homework, I think in the hand-in homework, I think it's 530, and I think that that's why I wrote it. If she does not survive, it's going to cost the insurance company $249,470 because that's the $250,000 that they have to pay out, but they did take in the 530. So I just subtracted the money, that 530 from it. So they're going to lose $249,470. And the probability of that happening, so all I did was took one and subtracted the 0.99791. I just subtracted that from one. So I used the complement to get that other number. All right. So this math right here is the random variable times the probability of that random variable happening. So this is the random variable times the probability of that happening. So I took, and this is or. So that's why we because you're going to get this or this or this. So that's why we're doing all of that. Don't worry about it. Anyway, so if I take the data, the outcome times the probability plus the other outcome times the probability, I get $7.50. So if we did a number of trials, so we look at all of the policies that they've sold to 49-year-old females, look at all of their policies, many, many policies, you're probably, if we have hundreds and hundreds and maybe thousands of women who've bought these policies, probably some of them are going to die. Therefore, the expected value of each policy is $7.50. So that's basically what each policy ends up being worth. So they're making a profit no matter what. So you're thinking about these thousands and thousands of policies that they've sold times the 750, they're still making money even if somebody dies. Questions on this? All right, I'm going to move on. Let's go back to the Netflix example. We're going to compute the expected value of the number of movies streamed per Netflix. So we're going to do this one together, and then I think I'm going to have you. I know. Okay. We're still going to do we will still do the oh, did we already do the basketball ones? Yeah, we did, didn't we? Because we already have the expected value of the Netflix. We're going to do the expected value of basketball. So just ignore the standard deviation stuff. I would like you to try this one. Try the expected value of the free throws. And I'm going to work behind you quietly. So start with this. How'd we do? So if we had this person many, many, many times try to shoot 3 free throws, it's really hard to say 3 free throws. We had him many, many trials try to shoot 3 free throws. He would average 2.36 free throws overall. So that would be the expected value. That's where we expect the average to end up based on these probabilities. This is so casinos use this type of math. They have expected values on every single one of their games, and basically the way that they calculate it is the for the consumer, they expect the value of their dollars towards the consumer to be slightly less than $1. They want it to be really close so that people think that they can win. But like, for example, if I went into play for the casino, my dollar is going to be worth like a dollar and maybe 8 cents or something. But to me, my dollar is going to be worth about 92 cents or 95 cents or whatever. So that way you can win enough to make you feel like that you can win big and come out ahead. But the house wins. I mean, do you think casinos would still be around if the house didn't win? So you know, probability wise, the house is going to win. And their expected values are such that they know that it's really close to $1 for $1, but it's in their favor just slightly. All right. Questions, comments, queries, concerns?
Would the 3 be multiplied by 0.51 or 0.5?
It's probably 0.51, so I must be slightly off. Man, I don't know what's wrong with me. It's this darn snow day. I'm going to fix it. It's going to be slightly different. It's 2.39 instead of 2.36. Thank you. See, you guys are becoming comfortable enough with me now to correct my math. I appreciate that. Please keep doing it. You like this math? Good. I do too. Expected value is one of my favorites. I say that about everything. It's like almost every math I teach, I'm like, yes, this is one of my favorites. But I like this. Okay, so now that we've done expected value, we're going to talk about standard deviation. So I'm going to go back a screen. We're going to talk about standard deviation. So I am not going to ask you to calculate standard deviation of a discrete random variable by hand other than one time. We're going to do it one time together. And then I'm going to show you calculator function for expected value and for standard deviation. So expected value, this looks really ugly. I know it does. So what we do with each one is we take your data value and you subtract the mean from it and square that. That should be familiar. But then you multiply that by the probability. You do that with each data value and then you add them all together and that's your standard deviation. I'm going to do it with the basketball data, and then I'm going to show you in your calculator how to do it. Okay. So I'm going to get rid of, we have our mean. So I'm going to take this right here and I'm going to move it up here so I don't lose it. And take this too, put that up there. All right. Let me erase all of this stuff. Okay, now I've got that out of the way. So what I'm going to do is I'm going to take each of these data values. I'm going to subtract the mean. I'm going to do the math all at once in my calculator, but I will write it out. So our standard deviation sub x, that's how the symbol for this. So it's going to be 0 minus 2.39. This is where my screens are different than what you have. But if you just go back to the basketball data, you could just do this on there. Squared, that's an ugly squared times 0.01 plus 1 minus 2.39 squared times 0.10 plus 2 minus 2.39 squared 0.38 plus, what have I got going on? 3 minus 2.39 squared times 0.51. I put the 51 this time. Put the whole thing in your calculator. Try not to typo. Okay. You put it in exactly how I have it with the parentheses, it should work just beautifully. I got 0.4979. Somebody check my math, please. So the standard deviation in this case means basically exactly the same thing as it means basically the same thing as when we were using the empirical rule before. 68% of my trials will be within one standard deviation. So 2.39 plus 0.4979 and 2.39 minus 0.4979. So in 68% of the trials, he'll make between 1.9 and 2.9 baskets. That's basically what the standard deviation is saying. And I know that it doesn't really make sense to make 1.9 baskets, but this is just, it is what it is. So it basically means the same thing. We don't use the standard deviation a whole lot with this. And so the variance, oh, was I supposed to take, I was supposed to take the square root of my answer. I just lied to you. Square root. I forgot the square root. See? Forgot the square root. This is the variance. I forgot to take the square root. My goodness, what is wrong with my brain? See, if I don't go to school during the day, totally messes everything up. Let's take the square root of that. Okay. Except for I see that my thing is slowed down a little bit. All right. Better. Thank you, Adrian. I appreciate it. As I always say, everybody has 5,000, at least 5,000 bad math problems in there. You got to do math to get the bad math problems out. So there we go. This is the standard deviation. Okay. Good thing we don't have to do it by hand, right? So this is the variance, or this is the variance. The variance is just the standard deviation squared. I have no good use for it. I've never had a good use for it, but that's what it is. Okay, so we're going to jump into calculator, unless there's questions here. Okay, we're going to jump to calculator function. All right, so let's go to our calculator. So go into stat, edit, go into your lists. I'm going to clear my lists out. We're going to do because we just did the basketball data, we're going to do that first. Okay. You're going to set this up exactly like your probability distribution table. L1 is going to be your outcomes, your data, your 0, 1, 2, 3 for the basketball data. And L2 is going to be the probabilities. So it's going to look like this. But there's not 4. Get rid of that. All right. And then 0 0.01, 0 0.10, 0 0.38, 0.51. Okay. So your random variable outcomes are your L1 and the probabilities are L2. Is everybody there? Okay. Then you're just going to go to one var stats. We've been here before. Go to one var stats. Your L1 is where your list is, and you're going to put L2 in your frequency list. So the probabilities, those probabilities are your frequency list. So when I hit calculate, notice that I got 2.39 for the mean, which is exactly that expected value that we had. So our expected value was 2.39. That's what we hand calculated. And then the standard deviation, yes, it only gives you the sigma, which is just fine. And this is exactly what we got, 0.7056. So this is the standard deviation, and this is your expected value. That's it. So it's super easy in your calculator. Questions on the calculator? Because we're going to do the Netflix data next. Then you go to, okay, so after you put your data in L1 and L2, go to one var stats, which is stat calc. It's the first one. And your regular list is L1, your frequency list is L2. Your probability is your frequency list. And then calculate. And bam. We're going to do the Netflix data next, just to make sure we have it. So once again, let's go to our lists. The cool thing is that all I have to do is add 4 and 5 down here. I just have to change the probabilities. If you don't have the PowerPoints printed out, you can just copy what I'm putting in here. If you can see it, I'll make it a little bit bigger. There we go. Not that I would trust me anymore. I'll give you a moment to get caught up if you were copying mine.
If this is on the hand in homework, do you want it to be shown then by hand or use the calculator?
So I don't ask for the standard deviation by hand. I do ask for the expected values. I would like you to do them by hand. None of them are big data values. None of them are like, I don't give you, I think one of them is 3, and then the other one is just like, it's just like the life insurance one. So they're really small. I would like you to show me by hand. I don't ask for the standard deviation because I don't find it super useful. Okay, so then go to stat.
Okay, thank you.
You're welcome. And one var stats, once again, your list is L1, frequency is L2, calculate. So we had calculated 1.49 for the mean. We did not calculate the standard deviation, but it's right down here. It's 0.9327-ish. So but you were able to get, how do you get the L2 second? 2. So down here, if you hit second two, that's how you get, that's where the L2 is. And whichever lists you're using, I frequently use multiple lists for different things. So it's, if I wanted the list 3, I would do second 3, list 6, second 6. So all your lists are just that, like that. Man, I can't speak. The expected value is the mean, yes. And no, it's okay. It's okay, Kate. But the expected value is the mean. And I believe that my open math uses them interchangeably. Sometimes they'll ask for one, sometimes they'll ask for the other. And I want to show you. So when they ask for expected value, they ask for expected value, it's going to look like this. Like this, like E of X. So capital E of capital X is expected value. So they might ask you to find E of X, and that's what that is. That's the expected value. Or it's the other way is like this, mu sub X. These are the same thing. Those are the same thing. Mu sub X or E of X, they're the same thing. And the standard deviation is just sigma sub X. My sigma is really ugly tonight. All right. Any other questions? Because that's it. And see, I told you we probably weren't going to be past 6:15 and it's 6:13 right now. So any questions on tonight's information? Let me see. You have everything you need to do the 6.1 homework. I think that 6.1 has its own homework. Let me check real quick. Okay. Yes. You have everything you need to do the 6.1 homework. So that's lovely. What else did I have to say? Okay. Yes. Okay. So yeah, you should be able to do that. So I want to give you the opportunity. I sent out the project, the final project, and I know it's super overwhelming since you don't have enough math to do it yet. So I know it's very overwhelming. But while we're still on recording, I wanted to open up the floor for if you guys have any questions. And I also want to show you, I'm going to go into student view because my view is crazy. So if you go into the final project folder, there is all of the final project assignments are in here. All the final project stuff is in this folder. So the final project proposal assignment, if you click on it, it's going to take you, yeah, okay, it's going to take you to, I didn't mean to do that in student view. It's going to take you here. You can just type it in right here. You just type it, give me a sentence or two, or if you wanted to submit a Word doc, you can. But if you just type it in here, and it doesn't have to be anything big and elaborate, you could just say, I really like dogs, so I wanted to do the age and weight of dogs, 20 dogs. I don't know, I'm making stuff up. But you tell me what you think your two variables are. If you want to give me 2 or 3 different ideas, I'll give you feedback on all of them. Super, super informal. Just say, I'm really into stocks and I want to look at compare compare Microsoft and Apple stocks over the last 50 years. I don't think they were both been around for 50 years. I'm making stuff up. But maybe 50 months, go back 50 months of Apple and Microsoft stock and compare them, whatever question you might have regarding that. Try to make it something you're interested in. The best projects are projects that are about things people are interested in, especially if it's something that you're passionate about. Those are always the best projects. And make sure you look at the examples. There's some fun ones in there. These are super fun. The in the presentation examples. These are super fun. And I bet you if you look through those, I bet you can figure out which two got extra credit. But I really love it. And just for the voter turnout one, the guy was like, "Can I do that? Is that one okay? Because I'm kind of being mean to people." And I'm like, "Yeah, go for it." The Super Bowl one, though, he purposely made it Broncos colors because he knows I don't like the Broncos. So he purposely made it Broncos colors. Fun fact about that particular student. All right. Questions? Okay, I'm going to turn off the recording.